Okay, this is the review for the final suite of midterms, I guess the finals, in week 15. All tests are closed book, closed notes. You can obviously provide your own calculator and pencil. The exams will be on Canvas in the comfort of your own surroundings, so you can choose the paper that you have available. And there'll also be the same equation sheet provided at the end of the exam, just like there has been on the other ones, which will comprise the material beyond this. They're all during class time, 8 to 8:30 on Monday, Wednesday and Friday in week 15, the last week of classes, and they follow the same format as other exams. The material covered is not comprehensive, it just covers the last material in the course. Really, pipes and networks, number 11.3, I guess, were networks, external flows, and open channel flows. And so those three topical areas, three chapters, 11, 12, and 13. The Monday test is a pipe flow question, which is a network. So you need to know something about the pipe flows. External flows is Wednesday, and open channel flows are on the Friday. And I think all the test questions are almost verbatim for previous tests that have come since 2019 and including 2019. So anyway, so the topical areas, energy equation, you know to write it from upstream to downstream. It can include a pump head. And Bernoulli's equation is elevation head, pressure head, velocity head. A pump head is power put into the system if it's positive, it's taken out of the system if it's negative, and downstream is Bernoulli's again. It has to be written upstream to downstream, as you know. And in the case where there's losses in the system, minor losses are due to bends in the piping and are given by a loss coefficient, which is a dimensionless number, and v squared over 2g. This is the average velocity in the fittings. And the major losses are due to friction factor, given by a Moody chart, friction factor, length over diameter of the pipe, and again the velocity squared term, velocity head term. The friction factors depend on whether it's laminar or turbulent. If it's laminar, it varies as a function of Reynolds number. If it's turbulent, it's independent of Reynolds number, but it has to be correct for the range of flows. Again, this flow velocity is the average flow velocity within the pipe. The pump head is given by a term which defines the power in watts, rate of doing work, gravity and the mass flow rate, or written in terms of volumetric flow rate, density, which is a mass flow rate, and gravitational acceleration. Friction factor has to be defined from something like a Moody chart. The friction factor varies as a function of Reynolds number, below 2000, Reynolds number of 2000 in the laminar regime. And so you need to define where the flow is, either as laminar or turbulent. And if it's turbulent, it varies not with Reynolds number, but does vary with relative roughness of the pipe. There are three classes of problems. The one that you have in your test, I think on the Monday, is in terms of a class 1, where you're given a flow rate and you calculate a head loss as a function of that. But the other problems are slightly more difficult because you have to iterate for a solution if you aren't given, for instance, a flow rate. If you're given a flow rate, obviously you can calculate the Reynolds number straight away. Reynolds number is a velocity, density, an equivalent length scale, usually the diameter of the pipe. For non-circular section pipes, it's the hydraulic diameter, d sub h, and a viscosity. And usually the solution method is to guess a Reynolds number, calculate a friction factor, use that friction factor to actually calculate a velocity from using the energy equation, and then check back that the Reynolds number that you used before is close to the other one. That's important, of course, if it's a type 2 or type 3 problem, but as I say, a class 1 problem you can solve in one step and don't need to go through that iteration. We made the point in class that internal flows and external flows are really quite similar in that they satisfy this Moody type chart, except instead of a friction factor, you're solving for an Euler number, an equivalent Euler number, which is the coefficient of drag or coefficient of lift. I guess this diagram isn't really quite right. This would be, maybe you should include that as a buoyancy force. So this is a buoyant force, which is equal to the volume that's displaced multiplied by the unit weight of the fluid. If it's air, this might be very small. If it's a liquid, it might be larger. Again, the Moody-like charts have a portion which, if it's laminar, below about a Reynolds number of 2000, is a function, the drag coefficient or lift coefficient is a function of Reynolds number, and if it's turbulent, then it's independent of Reynolds number. The coefficient of drag is defined, or lift is defined as a drag force divided by a half rho v squared times A. A is typically the planiform or frontal area of the structure, such as a sphere or an airfoil, which you're always told what it is, but it is an area that you have to accommodate. And you can rewrite this to define the drag force as a function of the coefficient of drag, which you would define based on a Reynolds number if it's laminar, or based on basically a constant if it's turbulent, and knowing what these other components are. Typically solve for the velocity as an unknown, where you know the area of cross-sectional area of your structure, you know the density of the fluid that it's falling through, you know a coefficient of drag because of the regime you're in, and therefore you can balance forces just by a free body. And so here you'd balance the weight of the particle relative to the buoyant force, and then there would be a drag force which would be applied on this, which would be your curly d value. And so you'd write an equilibrium equation between the buoyant forces and the weight and the drag force. Throw away the buoyant force if it's small, but keep it if it's perhaps in a liquid, and then solve for that. Again, the Reynolds number is defined as a velocity, the density of the fluid, a characteristic dimension. Typically for a sphere or a cylinder, it would be the diameter of that sphere or cylinder, and the viscosity of the fluid it's falling through. And you're solving really sum of forces is equal to mass times acceleration. Acceleration, if you set to be 0, it's just sum of forces are equal to 0. And so you can solve this free body diagram. And you can define the coefficient of drag as a function of Reynolds number. If you know it's a sphere, then it would be 24 over Reynolds number. And you could write the velocity in the coefficient of drag equation as a function of all the other terms, and solve for velocity as a function of the viscosity. And if you write the equation in the turbulent regime, you'd solve for v squared. Viscosity would fall out of the equation. You'd just be left with the fluid density, and you'd come up with square rooting your solution to be able to get the velocity. I guess I mentioned one of the questions is a pipe network. We talked about pipe networks as well. I guess I'm doing this out of sequence. Pipe networks, if you write your energy equation from upstream to downstream, by definition, since both of these pipes go from upstream to downstream, you could write Bernoulli individually through root 1 or through root 2, and you know that the head loss for each of these has to be the same because they're ending up at the same big volume tank with zero velocity. And so the sum of the flow rates in each of the pipes are additive, but the head loss between upstream and downstream have to be the same in both pipes 1 and 2. If you're flowing in a series flow where it gets progressively more constricted, from continuity you know that volumetric flow rate 1 and volumetric flow rate 2 have to be the same as it goes downstream, and so the head losses in these conditions are additive to each other. There'd be a small head loss in the big pipe and progressively larger and larger head losses in the smaller pipes. And for branching pipes, you can write Bernoulli from the upstream tank to the downstream tank through either this route or through the lower route. So you end up with two equations. Since the first part of those two equations is the same, the head loss between this midpoint and the downstream tank have to be the same in this particular flow. And so you can solve for the system of flow in those conditions. Week 13, I guess, or topic 13 was open channel flows. There isn't a uniform flow question this time, but if there was, you'd solve for defining the velocity as a function of the Shesi equation or the Manning equation with a constant, which is defined for SI units as 1, the Manning coefficient, which is really a roughness factor, which you get from a figure like this. Actually, it's always on the turbulent side. Hydraulic radius, which is an area over the perimeter. The area of flow is just the width of the channel and the depth, and the perimeter of the channel is just the wetted perimeter, which is given by this green curve here. And the Reynolds number would be defined in terms of a characteristic dimension, which would be the hydraulic radius, which you have here. And you could use this directly to get the average flow velocity as a function of hydraulic radius and the slope of the bed, which is just the drop divided by the length over which that drop occurs, which is relatively straightforward. There isn't a Shesi equation on the test, but there is a gradually varying flow equation. For gradually varying flow equations, we can write the equations for in terms of the flow per unit width of the channel, which is our lowercase q. And we can draw this specific energy diagram, which gives the depth of the flow as a function of the specific energy. And because a flow can organize itself with a free surface into a deep flow that flows slowly or a shallow flow that flows quickly, they both satisfy continuity, then the flow can either be subcritical or supercritical, depending on the flow regime. And so we can define that in terms of a specific energy diagram, where we define the specific energy as this uppercase E value, which is defined in terms of the criticality of the flow, and that's defined in terms of the Froude number, which is the flow velocity that occurs relative to the speed of the celerity wave in that flow. The speed of the celerity wave is just gravity times the depth of flow, square root. We did that maybe on the second time we met. The ratio of the actual flow velocity to that wave speed is a Froude number. If the Froude number is less than 1, because then it's a subcritical flow, that means the Froude number is less than 1. If it's supercritical flow, the Froude number is greater than 1, meaning that the high velocity flow is faster than the wave speed. Physically, what that means is if you dropped a pebble into the water for a Froude number less than 1, the circles would be kind of concentric. If you drop a pebble where the Froude number is greater than 1, then the ripples as they go downstream get progressively larger, but they're carried by the advection flow within the water. And if they're right at criticality, Froude number of 1, then they wouldn't be able to travel upstream because it's trying to travel upstream at exactly the Froude number, which is the wave speed. So that's the reason that you get these ripple formats. You can calculate the specific energy as a function of the depth of the flow per unit width of the channel squared divided by 2 gravity times the depth of flow. You get a curved surface like this, which conforms to this behavior, that at the critical flow, a Froude number of 1, where the flow is defined as critical, then this relationship holds, that the minimum energy is equal to 3 over 2 times the critical depth at which this flow occurs. And if you have, that will be the minimum specific energy. If the actual specific energy of your flow is different from that, has to be larger than that, then it could be one of 2 formats. It could be supercritical, flowing very quickly, but at shallow depth, according to this. If you draw this over here, you get this point here. Or it could be a deep flow that is flowing slowly and is equal to this magnitude here. And so knowing that the flow has to have the same specific energy if there are no losses within the system means that it has to be on this line. And so it could be either supercritical, flowing quickly and shallowly, or it could be subcritical, flowing deeply and not very quickly. And either of those are admissible. But to get from one to the other, you have to go through this nose. And we talked about in class having a bump on the bottom of the stream to be able to allow it to get through this nose here and to reorganize itself in some way. And so that's pretty much it. Okay, so that's it. This suite of equations that we've talked about should be everything you need for the test. Good luck on the 3 days of the test, and have a great time after you get out of this course. Hope you've enjoyed it. I've enjoyed having you. Take care. Thanks very much.